In this segment, we'll be discussing some of the issues related to measuring the correlation coefficient. The first one, the problem in interpreting the correlation coefficient, is the truncation of the range or hidden data problem. Um, Imagine if you're playing like a Little League sports. It's very easy to see the children that are really good at a sport or really poor at a sport. There's a lot of variation. When there's a lot of variation, it's really easy to determine what's considered as a success versus what's considered as a failure. And so we can kind of see in this graph that we have those individuals that aren't very good at the sport and those individuals that are very good, and there's a lot of variation. But as you get older, the lower end tends to drop out, and what you get is a truncation problem. And so the only ones that are left are those individuals at the very top. This commonly happens at especially elite universities that select only the top of any graduating class. Commonly, all of the students that go to those institutions are considered themselves A students. So it's very difficult for the instructors to differentiate between truly an A student and a B, C, or D student. So when we have this truncation or range problem, we have difficulty interpreting the correlation coefficients, especially if we have only selected the upper end of that scale. Where we did have a strong correlation between success and failure based on some measure, when we truncate the data, now we have a more difficult relationship. The second is the curvilinear relationship, or some other relationship that isn't linear. See, correlation assumes that two variables are linearly correlated or linearly related. When we have two variables that aren't linearly related, the correlation coefficient would actually be insignificant, or probably closer to zero. A good example of this would be performance on a test and the stress level. So a little bit of stress is helpful, and if we look at the bottom end of this scale, we can see that performance would go up as, there's a little bit of anxiety, you're kind of preparing well. But once you get past a certain point, that stress becomes debilitating, and we see that the performance actually goes down. If we were to draw a correlation coefficient between these two, we would probably find that there's no relationship, or we would get this flat line, and it would imply that stress level and performance are not correlated. Finally, correlation is strongly affected by an outlier. In the first example here, we have a relationship that is essentially there's no relationship between x and y. So the correlation simply indicates the relationship between two variables, but it does not tell us what caused the variables. Oh, excuse me, I'm getting ahead of myself. In the second example, we see that we have these outliers here. And so what's happening is it's going to actually create a relationship where most likely a relationship doesn't exist. So we have these two outliers that tend to pull that R, the correlation coefficient, up. And if we were to admit those two, we wouldn't see that same relationship. Number 4, correlation does not equal causation. Now this is critical. We'll highlight this idea because this is probably one of the most common mistakes when it comes to correlation and regression. So just because two variables are correlated, it doesn't necessarily mean that one variable caused the other variable. But we must be careful in using the correlation to indicate causation, because what might actually be happening is a third factor is actually causing both. So the most common example is that the ice cream example. So we know that ice cream sales are highly positively correlated with sunglass sales. What would you conclude? Well, your logic tells you that when people are buying sunglasses, it doesn't make them want to also buy ice cream. Your logic tells you that there must be something that's causing both the ice cream and the sunglass sales to go up. And this is most likely due to the presence of hot temperatures or brighter sun causing both of these sales to increase. So even though there is a correlation, we can't say that there's a causation. So how can we determine the causation? Control is essentially through experimental methods such as random assignments to experimental groups and controlling the other variables that might have an influence. Now, what does this really mean? It means that we need to use our logic. We need to recognize and first understand what might be causing the other variable. Then why do we do correlation studies if there isn't a causation relationship? We can't assign things randomly. That means that we can't just examine the causes increased by sales by randomly assigning them to different conditions. We have to have a theory. We have to kind of think about what might be causing these first or create a hypothesis. Number two, we need to maintain control. So lack of control, there are many variables that we can't control in the business setting. When we get into multiple regression in section 9, we'll be talking about control variables. And number three, correlation allows us to show relationships, but we can't make predictions. See, when we only have correlation data to draw our conclusions, we can only say that two variables are related, but we can't say that one is predicted by the other. This data will be very useful in a managerial setting where usually you can't do experiments. And we'll be showing you some examples in class of what we mean by that. So let's talk really quickly about the definition or the structural equation of the Pearson correlation coefficient. Pearson correlation coefficient is the covariance, how two variables covary, standardized or divided by the product of the standard deviations. I'm not going to expect you to calculate the covariance and the correlation coefficient in class. You'll be able to use Excel and other tools to do that for you. But I want you to recognize a couple of things. So in this example right here, we see that there is a positive correlation. We could kind of draw this line through this data and see that as y increases, x also increases. On average, there's some variation around that increase, but on average. This would be a positive correlation. How do we get a positive correlation? Well, in this equation up here, we see that if x is higher than its mean, this number would be positive. And if y was higher than its mean, this number would also be positive. A positive times a positive would give you a positive. If x, for example, let's say this number right here is less than its mean, y is also less than its mean. So this is the difference between x and the mean. This is the difference between y and the mean. We would see that the relationship here would be a negative times a negative, which is also a positive. So this would mean that there is a positive correlation. In the next example, we see that when x is above its mean, so let's take this point right here, and we can see that x is higher than its mean. Y, in this case, is actually, x is, I didn't grab a very good example. Let's grab this one right here. So x is above the mean right here, or below the mean. Y is above the mean. So in the previous example, we would see that this would be a positive times a negative, and that would give us a negative correlation coefficient. If x is above the mean, y is below the mean, we get a negative times a positive. If x is below the mean and y is above the mean, then we get a positive times a negative. Now, another problem. Covariance depends on the units of scale of the two variables. We need to standardize with respect to the scale of these two being used. This is why we divide by the standard deviation of the product of the two. So the standard deviation is in the same units as the covariance. So the correlation coefficient is essentially a unitless number because we divide by both the units of x and the units of y. Now, might sound a little complicated, but I want you to use your intuition when we talk about correlation coefficients. Financial example here of covariance. If you steer clear of the math supporting the theory, covariance is relatively a simple concept. According to Investopedia that I commonly use in my finance classes, covariance measures the degree to which returns on two risky assets move in tandem, or they move together. If there's a positive covariance, or correlation coefficient, it means that the asset returns move together. A negative covariance means that the returns vary inversely. So the idea for money managers, we want to simply add assets that have low covariance because when one asset goes up, the other asset goes down, and we can reduce or decrease the overall risk in the portfolio.